Hello, on today's episode of EECS 2021, we'll be converting a floating point integer to IEEE 754 single precision format. So to begin, we can start with the left side of the decimal or the whole numbers. So we'll just take 63 and we'll convert that to binary, okay? So how I like to convert to binary might be different from you, so you can convert this however you would want to, but this is how I convert stuff to binary. So I start 2 to the power of 0, which is 1, or actually I'll write it like this: 2 to the power of 0, which is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, 2 to the power of 4 is 16, 2 to the power of 5 is 32, 2 to the power of 6 is 64. We won't need further than this, but notice how if we were to continue, the exponent of the 2 is simply what keeps incrementing. And so whenever you increment it, you can just take the last value and add it with itself. For example, 32 plus 32 is 4, 3 plus 3 is 6, so it's 64. And if we wanted to continue, 64 plus 64 is going to be 128, so on and so forth. So 2 to the power of 7 is 128. All right, so now that we know that, we're going to take 63, and we can notice that 32 goes into 63, so we'll take 63 and subtract 32, and we'll be left with 31. Okay, and since that 32 goes into 63, we'll put a 1 there. We put zeros here because those don't fit. Next, 31, we know that we can tell that 16 goes into 31, so we subtract the 2, so we can just borrow 1. That's going to be 11 and 2, so 11 minus 6 is 5, 2 minus 1 is 1, so now we're going to have 15. Let me write that a little nicer. Okay, so we'll write a 1 there. Then we notice 8 goes into 15, right? So that's going to be 7. Okay, we'll write a 1 there. 7 minus 4, that's going to be 3. So 4 fits, so it gets a 1. And then we're going to have 3 minus 2, and that gets us a 1. So we're going to have 1 minus 1, and that gets us to 0. So that's basically how I convert to binary. There's other ways. Some people like the division way, so you just take 2 and you divide it by 63. So so it would be 62 with the remainder of 1, so that's going to be 31. Right, 31 plus 31 plus 1, yep. So then we take that, divide it by 2, and you can continue on like that. Okay, but I've already converted it, so that's great. So now let's focus on the decimal part. So I'm just gonna use the power of technology to move this. So for the decimal part, we have 0.25, okay? And then you're gonna multiply it by 2. This is the trick, okay? So when you multiply it by 2, we're going to get 0.5. And you're going to want to keep track of the ones, whatever digits in the ones position. So here we have a 0, so we're going to write it as 0. And then we're going to take this and move it over here, so it's going to be 0.5 and multiply it by 2. When you multiply it by 2, you're going to get 1.0, and since we have 0 left as the decimal, we're going to stop here and just take the 1 and move it over there because that's in the ones place. And so finally we can write this entire 63.25 is represented as 1, 1, 1, 1. So these ones, 1, 1, 1, decimal 0, 1. Okay, so going forward, the next step is to simply shift this decimal over here. And similarly, if we were to write scientific notation in decimal, you multiply it by 10, but because we're in binary, we're multiplying it or dividing it by 2. So that's how we're going to write it. So it's going to go 1. So the decimal place is going 1, 2, 3, 4, 5 increments. So we're going to have 1 decimal 1, 1 decimal 1, 1, 1, 1, 1, 0, 1. But this time we have to write multiplied by 2, and the exponent is the number of times we moved it. So it's going to be 1, 2, 3, 4, 5. So 5 for the exponent. Okay. Next we have our what's next? So since this is 32-bit, we have to incorporate the bias. The biases are different for 32 and 64-bit. The bias for 32 is 127, if I remember correctly. Yeah, that's 127. And then the bias, if this was 64-bit, it's going to be 1023. Okay, but this is 32-bit, so we'll just ignore that. Okay, going forward is we're gonna have to take that and we're going to add 127 to it. Okay, so we're gonna simply add 127 plus 5, and that gives us 132. Okay, okay, great. So how we represent this in 32-bit, this number is we have 32 bits. So we're gonna have some bit there, and then we're gonna have 8 more bits. So that's 4, 5, 6, 7, 8. And then we're gonna have the remainder. And this continues all the way to the 31st bit. So this is the 0th bit, and this is the 31st bit. Okay? So our first bit is the sign representation. Okay? So we know that it's going to be our sign representation. And then the next bits, this is our exponent. And we get our exponent as 132. So you take the original one, you add the bias, and that's our exponent. And finally, we're going to have all of these bits. And these bits are everything after the decimal, okay? Everything after except the 2. So all of the binary digits after the decimal is what this is. And this is has a funny name. It's called mantissa. So this is our mantissa. Okay, so since I explained that, we're simply going to convert this 132 again from decimal to binary. Okay, so again, I'm going to use the help of technology here by copying and pasting all of this information. Save us a little bit of time. There we go. So 132. I don't know what that was. 132 to binary. Okay, so again, we know 132 and 128 fits there. So, oh, and also I just noticed something. This is a full 8 bits. So that's great. So 128, it fits. So it's gonna get a 1. And we're just gonna subtract them. So we have to borrow 1. So 12 and 8, that's 4. 2 and 2, that's 0. 1 and 1, that is 0. Wow, that's awesome. Okay. Next, we have. Is it actually? Let me just make sure with the calculator. It's like this on exams, to be honest. 128. Yeah, it is 4. Okay, awesome. So what goes next is there's a 4 there, and then we're gonna have some zeros in between. Okay. So we'll have some zeros, and then 2 more zeros at the end, and that's our full 8-bit representation of 132. Okay. So let's just write this up here for some clarity. We'll have 1, 0, 0, 0, 0, 1, 0, 0. 1, 2, 3, 4, 5, 6, 7, 8. Yep, that's an 8-bit representation. Okay, so that's great. Now that we've done that, we can write our final form. So our sign bit, it's a positive 63.25 is positive, so we're going to write that as a 0. And then we're going to take this, because that's our exponent, and that's going to be 1, 0, 0, 0, right? Those 4 bits. And then we're going to have 0, 1, 0, 0. And then it's going to be our mantissa. Okay, so our mantissa is there. It's going to be these 4 1s, so it's going to be 1, 1, 1, 1, 1, and then 1, 0, 1, 0, 0, dot, 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 dot. And the remainder is all, like all the other bits are zeros after that. Okay? So this is the mantissa. This is the sign bit, and it's positive. And here is the exponent with the bias, of course. All right, great.